Okay, so today we'll be discussing week 8 uh, problems. And what was discussed in week 8 was, so what was discussed in week 8 was tangent cones, and then some properties of tangent cones for constraint optimization settings, and then constraint qualifications. How the tangent cone is defined uh, for a point when the constraint qualification is satisfied. We looked at the linearly independent constraint qualification LICQ. Then we looked at the KKT conditions. For local minima. Then we looked at then you move to convex optimization and discuss the theorem where it was shown that when if a point satisfies the KKT conditions in for a convex optimization problem and the complementarity slackness condition, then that point is also a global minimum for a convex optimization problem. So we'll discuss some problems related to week 8. So I changed the format a bit. So from last two classes, I think no one has been attending the live session, so I've sort of not discussing any new problems from other books. What I'll be discussing is I'll be discussing the assignment questions from last year. Okay, so they are very much similar to the assignment questions which are given every week. So I'll discussing the week 8 assignment questions which was there in the NPTEL course offered last year. Okay, last year or last to last year, so that one. The same assignment questions I'll be discussing. So they may be varying only slightly from every week's assignment questions. So this is the week 8 of last year. Okay. So this question is saying, so I just discuss these questions. So the first question is, consider this problem where you have f of x of your objective and some set of constraints is given, and they are asking how many constraints are active at a point x star equal to 1 comma 1 transpose. So if you have some constraint gix less than equal to 0, then we say it is active if gi it is active at x star if gi of x star is equal to 0. So we just need to do, like, what we need to do is we need to substitute this point x star in each of the constraints and see where the equality holds. So x star is 1 comma 1 transpose. So if I look at the first constraint, I have 2 plus 5 which is equal to 7. So this is active. Look at the second constraint. I have 3 plus 1 which is equal to 4, which is less than 6. So this is not active. Look at the third constraint. I have 7 minus 2 which is equal to 5. So this is active. Look at the fourth constraint. I have 1 plus 9 is equal to 10. So this is also active. So except for this and this are active. So how many constraints are active? 3 constraints, right? Since we have only 4 constraints, the answer can only be less than equal to 4. And since one of them is not active, we have 3 constraints which are active. Okay. Now let's move to the next question. So this question is asking if we have this problem, this object unconstrained optimization problem, where f of x is defined via these two variables. Straight true or false, 1, 1 transpose is a local minima. Okay. So how do you check that? So one important required for a local minima is the gradient at x star, that should be equal to 0. So let's look at the gradient. Like if x star is local min, then this should be satisfied. Okay. So what is the gradient? Gradient is 2x1 minus 8x2 and 4x1 minus 8x2 plus 6x2 minus 8x1. Okay, so the gradient of f at x star I am calling it is 1, 1 transpose. Gradient of f at x star is 4 minus 8 6 minus 8, okay, which is minus 4 minus 2. So this is not equal to 0. So this is not a local minimum. So the answer is false. So how do we, if the gradient would have been 0, would that be sufficient to conclude it's a local minimum? If the gradient is 0, then the necessary condition is satisfied, but we'll have to look at the Hessian also at that point to say whether it's a minima or not, right? The Hessian has to be positive definite. Only then we can say whether it's a global minimum. sorry, local minimum dot. In case the gradient were was 0. Okay, so let's look at the next question. I have this set S, which is defined by this. It has two variables. A set of 2D vectors, and x star is given. Which of the following are contained in the tangent cone? Okay, so let's recall. We have tangent cone defined uh, for this point x star on this set S. Okay, so let's try to recall the definition of tangent cone. So a tangent cone x star is, it was defined as the set of directions D such that there exists a sequence xk in S. Xk in S, and xk tends to x star I think I should write the xk in S and tau k in 0 to infinity such that xk tends to x star, tau k tends to 0, and d is equal to the limit k tends to infinity xk minus x star and tau k. So this is the definition of the tangent cone. But we need not find such things. A more simple definition is, a more intuitive way to understand this, we have some convex set, and if we have a point here, then we have a tangent. The tangent with respect to this is our S. Okay, the tangent at x star with respect to S will be the directions in this way. Okay, and if x star is here, then the tangent for this x head will be the Rn, where x hat is in Rn. Okay, and if so, if constraint qualifications hold, holds at x star, then your tangent is defined at Like if your S is gi of x, this is then equal to 0. Gives constraint coefficient holds at x star for this S. Then your for all I in the active set, like this. Okay, so this is the active set. The active set we had seen in the last. For all the constraints at which this GIX is active. And constraint qualification, we had learned one type of constraint qualification, that is LICQ. Linearly independent constraint qualification, which means the gradient gi x star in are linearly independent. Okay, so if this holds, then we have constraint qualification which holds. So then the tangent cone is defined as this. So this we can check in this case. So if you look at this set S, you have one inequality constraint, and it is basically a circle with radius 2. And what your x star in this point. X star in this point. So the tangent cone will be this basically. And the constraint qualification, does it hold? You can say it holds. There is only one constraint, one active constraint, which is x1 star square plus x2 star square is equal to 4. And if you look at the gradient is 2gix star 2x, which is basically 0, 4. So you have only one gradient. You can say g of x. There is only one gradient, so it's linearly independent. So your tangent set is d such that 0, 4 d is less than equal to 0. Okay, so this will be true for d is of this form, d1, d2, then d is in txs for all d1 in r and d2 something by mistake. D2 less than equal to 0. So if I multiply this by this, I'll have 0 4 d is basically 4d2, right? d1 d2 4d2, and if d2 is negative, then this is negative. So I just need d2 to be negative. And what we have is only D option satisfies. D2 is negative. So this is there in the tangent code. Okay. That is this question. Because there was only one constraint, so we don't need to check for the linear independence of the gradients. And this point was on the boundary. So here we are having another set in 2D, and we are given one point, and we are asked whether the tangent cone is R2, true or false. So let's look at this set. It's 2D, so we can just draw the set. X is between 0 and 1. 0 and 1. So the set is something like this, right? It's between 0 1, 0 1. And my point is this point 5. This is my X star. So because it is in the interior, so the tangent from this R square, because I can come from any direction to this point. Okay, I go to any direction from here, I'll be in the feasible region only. But in the other case, there is a set of directions only in which if I go, I'll be in the feasible region. Okay. So this is false. Oh, sorry, this is true. This is correct. If the point was somewhere here, then the feasible directions would have been something like this. If it was on this edge, then the set of directions would have been something like this here. Actually, all these would have been there. Yeah, all directions. All this one. Okay. So when you go to the next question, consider the problem and minimize f of x x star equal to 1 2. State true or false. LICQ is satisfied. Okay, so now we have an objective function and three constraints. We just need to check whether LICQ is satisfied. Hit this part. So I need to look at the gradient. So let me look at the gradient of the first function, which is 3 2. This is the gradient. Okay. And then I need to check it only for the active constraints. So is this active? 3 plus 4 is equal to 7. Here I have 1 plus 12 is equal to 13. Here I have 5 plus 4, which is equal to 9. So I just need to look at these two constraints. So the first constraint I got this. Second constraint I have 1 comma 6x2, which is equal to, like, the gradient at x star is equal to 1 by 1 comma 12. And you can see they are linearly independent, right? So 3 lambda 1 plus lambda 2 equal to 0. 2 lambda 1 plus 12 lambda 2 equal to 0. This only holds, only true if lambda 1 equal to lambda 2 equal to 0. Okay. So LICQ is satisfied. They are linearly independent. Go to the next question. Consider a convex function f straight true or false if x1 star x2 star are two local minima of the function. Then fx1 star is equal to fx2 star. So we need to say if x1 and x2 are local minima of the function f, then fx1 star is equal to fx2 star, true or false. So in general, for some f, fx1 star to fx2 star, not always true, right? For some general if. For some general if this is not true, because some simple is like this. These two are x1 star, x2 star. They are not equal. But what we have is convex f. So convex f then this is true. Yes, local min is equal to global min, and it can be easily shown because you have for convex f we know f of fy is greater than equal to fx plus gradient of fx dot product with y minus x for all xy. Okay, this is true. So at x equal to some x1 star, then f and gradient of fx 1 star is equal to 0 as it is local min, right? So f of y is greater than equal to f of x1 star for all y, which implies x1 star is global min. Okay, so this will hold true for all local min. So all local min are global min. So that means the function value is same. So this is true. The next question. What I have is we have some function f of x equal to max 1 minus x 0, and this is also true or false question. We are asked whether this has a unique global unconstrained minima. So this is a single variable function, so you can easily plot this. At x equal to 0 it is 1, at x equal to 1 it is 0, so you have a line like this. For x greater than 1 it is 0. Okay. So it's something like this. This is your function. So the global minima is at all these points, right? So it does not have a unique does not have a unique global minimum. All x greater than equal to 1 is global minimizer. Of course, the global minima value is unique and the minimizer is not unique. So if they mean minimizer, then false. The minimum value is not unique. Okay. I mean minimum value is 0 everywhere. So minimum value is always unique. Yeah. Global minima is always unique. Local minima may not be unique. Okay, so consider f. We have some point x star at which gradient is 0. Which of the following are correct? If f is convex, then x star is a local minimum. So that we know via this, right? This is true for all. For convex f, this is true. So delta f x star equal to 0 means f of y is greater than equal to f of x star. So x star is global min, which is also local min, right? So A is correct. If is non-convex, then x star is local minimum. That need not be true. Can be global maxima, local maxima for non-convex function. Right? This is also gradient 0. But local max, non-convex function. If is convex, then x star is global minimum. So this is also correct. That is what we should have shown it. If f is non-convex, then x star is global minimum. This is incorrect. So these two are incorrect. A and C are correct. Okay, this question. So you have this some S1 is given and some S2 is given. In 2D, both have one constraint, and x star is some 2D point. Each of the following points are contained in the intersection of the tangent cone of the intersection of S1 at S2 at point x star. So this in 2D, so we can draw this is basically a circle at the point 0, 2. Of radius 2. Okay, this is S1, and similarly S2 is a circle here with center here. This is S2. So this is their a point of intersection. This is S1 intersection. S1 intersection is 2. So the tangent here for a singleton point, tangent will also be singleton, right? It will be 0 comma 0 only, because your xk sequence, it should be in S, xk will be 0 comma 0. So your d, which is equal to limit k tends to infinity xk minus x star upon tau k, this will be 0 only. Because xk is 0 comma 0 and x star is also 0 comma 0 and tau k is some positive scalars. So this will be x. Okay. Let's look at this question. You have 2 points x star and x double star. They are the local minima of a convex function f of x. Then which of the following are global minima of f of x? So we are given f of x is convex. So we know that x star and x double star are also global min of f of x. So they are asking which other points are global minimum of f of x. So this and this are global minima, that we know. We need to check whether these and these are also global minima. And it's easy to check because we know alpha x plus 1 minus alpha x is less than equal to f of x plus 1 minus alpha and x1 x2. And alpha n 0 for convex f. So if I put 0.2, 0.8, what I'll get is f of 0.2 x star plus 0.8 x double star is less than equal to 0.2 f of x star plus 0.8 f of x double star, and we know f of x star is equal to f of x double star as their global mean. So that means f of 0.2 x star plus 0.8 x double star is less than equal to f of x star, because 0.2 plus 0.8 is 1. Okay, here one more condition is there. Oh no, this is the only condition, because alpha plus 1 minus alpha is 1. So you have this, and this implies f of 0.2 x star plus 0.8 x double star is equal to f of x star as f x star is global mean value. Okay, so this can't be less than f of x star, because f of x star is the global minimum. So this is equal. So this is also global minimum. So these two are also global minimum, because you can do the same thing with 0.8 point. Okay. Next question is, we have this optimization problem, and x star satisfies the KKT conditions. So here what we have, x star satisfies the KKT conditions. It means that, what was the KKT condition? This is the KKT condition. X star is global minimum of the optimization problem. So we know, for convex f, if x star satisfies KKT, then x star is global min. For convex f and g, so we just need to check whether they are convex. So the first problem is as a quadratic. So it will be convex, right? You can just check if uh, check the convexity by looking at the Hessian, right? So if I look at the gradient, it is 2x1, sorry, 4x1 and 6x2, and the Hessian is 4006. Okay, and this is positive definite because we take any this is positive definite is V transpose 46 V is greater than 0 for all V not equal to 0. Okay, this was F. So F is convex, and this is a linear function. So this is also convex. A linear inequality is convex. The linear equality is also convex, and inequality with a convex function is also convex. But inequality equality with a convex function is not convex. So we have an inequality, a linear inequality, so it is convex. So our constraints are objective, both are convex. So if x star satisfies the Kiketi condition, then x star is also the global minimum. So this is true. So we'll discuss this last question. We have this f in objective with two variables, and we have two constraints, and then given this x star is the optimal solution. And what is the optimal function value, optimal objective value? Okay, so we can see like this is a convex objective, convex, also convex. So a convex optimization problem. So then implies that KKT counts. So let's look at the KKT conditions. So we need delta f of x star plus lambda g of x star plus theta gradient of h of x star is equal to 0, and lambda should be greater than 0, and theta is 7. So this is 2x1 star plus 2x2 star plus lambda into 2. Well, I need a gradient, right? So gradient is what? 2x1, 2x2. Yeah, sorry. Is lambda times 2, 1 plus theta times this is equal to 0. Okay. So we have 4 variables and 2 equations. We have one more equation, that is x1 plus x2 is equal to 2, and one more equation we get from complementarity slackness, that is lambda g of x should be equal to 0. Okay. So lambda to lambda x1 plus lambda x2 minus 3 is equal to 0. Okay, here it should be minus, because I need a constraint should be less than equal to inequality. So I'm going to write this as plus minus minus. And this one I'll write as 3 minus 2x1 minus x2 less than equal to 3. Okay, because we had defined this for min of f of x, g of x less than equal to 0 and h of x equal to 0. So we try to use these two equations. So I have 2x1 minus 2 lambda plus theta is equal to 0. So x1 is equal to 2 lambda minus theta by 2, and 2x2 minus lambda plus theta is equal to 0. So x2 is equal to lambda minus theta by 2. Okay. And I also have this, right? x1 plus x2 is equal to 2. So that means 2 lambda minus theta by 2 plus lambda minus theta by 2 is equal to 2. So 3 lambda minus 2 theta is equal to 4. So what I can do is I can write everything in terms of lambda by writing theta equal to 3 lambda by 2 minus 2. Okay. So then if I use this equation, 2 lambda x1 x2 so I can write 2 lambda x1 is okay. So let me first write x1 is 2 lambda minus by 2 which is equal to 4. 4 minus 3 is lambda and x2 is lambda minus, okay, this should have been plus 1 lambda minus 3 lambda by 2 plus 2 1 minus lambda by 4, right? So I can substitute now x1 and x2 in this. Which gives me sorry, here also I have 3 lambda. This is lambda gx, so 2 lambda x1 plus lambda x2 minus 3 lambda equal to 0. So lambda here also. In this case, my lambda square by 4 equal to 0, which implies lambda is equal to 0. Lambda equal to 0 implies theta is equal to minus 2. So x1 is equal to 1 and x2 is equal to 1. So f of 1 comma 1 is equal to 2. So what we need to find, what is fx1 star x2, that is equal to so we used KKT condition. This is the equality constraint. This is complementary slackness. And with that we got all these equations. We had 4 variables, 4 equations, and doing some gymnastics, like swapping here and there, we got x1 and x2. Okay. Yeah, so these are some problems from week 8 where we used we'll use some ideas of tangent cones, and then the KKT conditions, convex optimization, how having the KKT condition implies that you have the global minima. The local minima is the global minima for convex optimization. That is it is. Okay. So I'll stop the recording. Maybe I'll ask in the Google group next time for you to post some doubts or questions that I can discuss in the next class. I plan to do it in the last week also, but I forgot. So next week I maybe 3 days back before the live session I'll post in the Google group, so you can ask your doubts which I can discuss in the live session. Okay, I'll stop the recording.